So multiply both sides of that by cosine theta. You'll get sine of theta is 4/5 cosine theta. So here's what I'm going to do. I'm going to try to write down two different equations. I'm going to use this and another factor by tree functions to get all the information I need. So one is always the same thing as sine squared plus cosine squared. And I already know the sine. The sine is 4/5 times cosine theta. So if you make that substitution, you'll wind up with 1 is equal to cosine squared theta plus 4/5 sine theta squared. Nope. Because sine theta is the same thing as 4/5 cosine theta. So if you just make that replacement, there's what you get. Is that now an equation that you could maybe solve for cosine? Yeah, let's go through the motions of doing it. So the equation right now is just 1 is equal to cosine squared theta plus 4/5 cosine theta, quantity squared. And let's start by just simplifying. What does 4/5 cosine theta quantity squared simplify to? Cosine squared? Right. Exponentiation distributes over multiplication and division. So 1 is equal to, I'll leave myself some space there, 16/25 of cosine squared theta. And now notice, I'm going to be able to factor out a cosine squared in a moment. So maybe I'll even set myself up so I have a good common denominator to use. And so now I'm going to simplify that until it's easy to solve. So let's see, the cosine squared I can factor out. So I'll see cosine squared theta, then 25/25 plus 16/25. 25 plus 16 is 41/25. And that's equal to 1. And I want to solve that for cosine of theta, because I want to know what cosine of theta is. And now it's like automatic, right? Divide by whatever's next to the cosine, or I guess multiply by its reciprocal, and then take a square root. So what do we wind up with? We wind up with cosine theta is, well, let's see, with the square would be 25/41. Then we take a square root, plus or minus. When we see plus or minus 5/41. And let's decide between positive or negative. So this angle is inverse tangent of 4/5. What's the range of inverse tangent? Look at the front page of this note packet if you need to know my help. The zoom type. What's the range of inverse tangent?
Negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. What quadrants do those trace out? That's quadrant 1 and 4. Okay, nice. So this is quadrant 1 or quadrant 4. In quadrant 1 or quadrant 4, is cosine positive or negative?
Cosine is positive.
Cosine is positive. So we get 5/41, which we already know is going to simplify down to 5/41/41. How do people feel about that? So there's another approach to this thing. You can draw a line triangle, see where the pictures lead you. There's a small danger in that you should be careful about signs. That just amounts to checking quantities. Otherwise, you can translate everything to just algebra and do things purely algebra. Are you pretty happy about this? Cool. So in some sense, this completes the main goal of yesterday's lecture. What I'd like to start doing is using these things for the purpose they're intended, and that's solving trig equations. Let's solve some trig equations. In particular, here's one. Let's try to solve the equation cosine of theta is equal to 1 over 3. And let's see. You see here the graph of cosine theta, and you also see a line at y equal to 1 over 3. By looking at this picture, how many solutions to that equation should there be? Infinite. So we expect some infinite family of solutions. So whatever the solution we get, there'll probably be like a plus 2 pi k going around or something. Let's try to do that. Let's try to find these solutions. So I guess here's one. If you think about inverse trigonometry, can you give me the name of an angle whose cosine is 1 over 3? Inverse cosine is 1 over 3. Will that do the job? So, right, because remember, so here's one solution. One solution is theta equal to cosine inverse, or arc cosine if you happen to prefer, of 1 third. And let's even highlight that solution. So that's the solution that lives somewhere between 0 and pi. So let's try to indicate it on this graph somehow. So I see 4 solutions here already. 1, 2, 3, 4. Which one of them is the inverse cosine of a third? That's the third one. Oh, right, that's the one that's between 0 and pi. So let's highlight the solution, and let's I'll draw a little star. So there's the point that will be called star. There's the point, the solution at cosine inverse of a third. Is that the only solution to that equation that you see? So here's one thing you could do. That solution is definitely going to produce a solution if you shift it by 2 pi, or 4 pi, or negative 2 pi, or negative 4 pi. So here's one infinite family of solutions we'll get automatically. So one infinite family of solutions to cosine equal to 1 over 3 is given by cosine inverse of 1 third plus any multiple of 2 pi. That'll give an infinite family of solutions. And let's just draw a picture and see if that looks like it's all of them. So there's this one. If you shift it by 2 pi, it'll be over there somewhere. If you shift it by negative 2 pi, it'll be that solution. In the meantime, did I skip any of the solutions when I drew those dots? Yeah, I missed like 2 items. I missed that solution and I missed that solution. So let's see how we can indicate those solutions. And one way to do it will be, well, I guess thinking about the units also. So there's the angle you already found. There's the solution to x equal to 1 over 3 that happens to live in quadrant 1 or quadrant 2. So there's an angle of theta equal to cosine inverse of 1 over 3. And you see the other angle now, right? We're interested in cosine. Cosine is the x value. There's an x value of 1 third. There's a point of intersection. There's another one. How could you describe the angle that generates this point? an angle with a different angle that reflects the point over the x-axis. Adding or subtracting pi over 2. Not quite, right? So subtracting pi over 2, that would shift this. Right, that would achieve like a reflection over the line y equals x, which isn't quite what we want. Sorry, this is the, well, even that's a slight lie. So not pi over 2, but what if we want to subtract theta from 2 pi? What would that do? What if we want to go forward all the way by 2 pi and then backward by theta? Would that give us this angle? So let's try that one. And this isn't the only one. So here's another solution. Here's another solution. 2 pi minus inverse cosine of 1 over 30. That would give us another solution to the equation, right? How many people would rather just use minus inverse cosine of a thought now? That would also do the job, right? Instead of rotating forwards by 2 pi and then backwards by inverse cosine of a thought, you could just rotate backwards by inverse cosine of a thought. Nice, and let's see, I'll use this solution. If you want to use the green one, well, I'll highlight both. What's another symbol? Triangle's another symbol. So let's indicate 2 pi minus inverse cosine of a thought. So let's see, the angle we started with inverse cosine of a thought is between 0 and pi. If you take something between 0 and pi and subtract it from 2 pi, you'll get something between pi and 2 pi. That seems reasonable. So this next solution we found will be the solution to the equation that's between pi and 2 pi, which is, I think, this point. So there's the solution to the equation that is called triangle. If you're the type who prefers, oops, I lost a minus sign. That one, box. There's the solution that's called box. Nice. So either way, once we found these two solutions, either one of those two solutions, we can get the rest of the solutions by adding 2 pi's to them. So we already had half of the infinitely many solutions. The remainder is, I'll continue to use this one. It's not important that I do. 2 pi minus inverse cosine of a third plus 2 pi k. Gives me the rest of the solution.
You could just say like negative cosine and invert cosine number.
Yep.
Okay.
Yeah, that is equally valid. I guess the only reason, so whether you think this answer is better than that answer is whether you prefer the answer that has fewer symbols, or whether you prefer to find the first two positive solutions. How do people feel about that? Does it seem okay? So if you want to solve some trig equation involving cosine, first find one solution to the equation. Maybe you'll need to use inverse trig functions to do it. After you find one solution to the equation, find another one by doing some reflection. Yeah? That was supposed to be a plus, but then I tried to cross it out. I was going to write plus 2 pi k, but then I noticed that I already had it in the document itself. Cool. So first find one solution. Then find a second solution by reflecting over the x-axis. Use one of the symmetries of trig functions. Once you find those two solutions, find all the rest of the solutions by adding 2 pi k's. How do you feel about that? Does it seem okay? So I know I handed you out a note packet that has more examples, but I want to go through all three of the ones in this packet first. So, let's try to play the same game. Let's try to find all of the solutions to sine of theta equal to negative a half. I guess false things false. How many solutions does it look like there are to this equation? There are infinity solutions. And it looks like they have a nice periodicity. It looks like they repeat every 2 pi, and during any given period of 2 pi, it looks like there are 2 solutions. So the plan will be the same. Find 2 solutions to this equation. And once you find those 2 solutions, then add 2 pi k's to them. So let's try to do it. What is one solution to the equation sine of theta equals negative 1 over 2?
Inverse sine of negative 1 over 2.
Inverse sine of negative 1 over 2. And I'm leaving myself some space here because there's one thing that I want to point out. On the other hand, is negative 1 over 2 an input where we know what inverse sine is equal to? Sorry, I shouldn't phrase that as a question when I'm obviously saying what the answer is. Yes, this is an input where we know what inverse sine is equal to. Either by looking at a unit circle, or by looking at that table of lookup values for inverse sine that we generated a while ago. What is the inverse sine of negative 1 over 2?
Negative pi over 6.
I thought of negative pi over 6. Is that also what you said? So like 2 equals 2.
Negative pi over 3.
Negative pi over 3. Nice. So there's controversy then. Let's try.
It's negative pi over 3.
Okay. The controversy is resolved. Does anyone want me to try the unit circle anyway and say why it's negative pi over 6? Okay, let's try unit circle anyway. Let's see, I'm going to draw as little as possible. I want sine equal to negative a half. So, and I know I only want the ones that have quadrant 1 or quadrant 2, and I want when sine is negative, so I'm only going to draw, quadrant 1 or quadrant 4. I'm only going to draw quadrant 4. So, I mean, whenever you want to fill in the unit circle from scratch, you can kind of just know that the only numbers you see are 1 half, root 2 over 2, and root 3 over 2. And then you just need to put them in increasing or decreasing order. And I want to see now when is sine, that's the y value, equal to negative 1 over 2. That's this number. And you might say by looking at your unit circle that that's an angle of 11 pi over 6. And on the one hand, if you look at the original question, solve that equation, you could just write 11 pi over 6 and have a solution to the equation. That would be fine. But if you want the solution, which is the inverse trig function, because I've already written down inverse sine of negative a half, well, that has to be the number that's between negative pi over 2 and pi over 2. And instead of rotating forward by 11 pi over 6, it's rotating backward by negative pi. Cool. So that's the answer to this equation, the solution to this equation, which happens to be between negative pi over 2 and pi over 2. So that's like the closest solution to the origin that there is. There are 4 points of intersection up there. Which one of those points is the point at x equals to negative pi over 6? The one closest to the origin. So I guess that's this one.
Nice.
And so now you already know infinitely many solutions to the equation now, because you just add 2 pi's to this.
Negative pi over 6 plus 2 pi would be over there. No, the green color is that one. It should be black. There's negative pi over 6 plus 4 pi, and you could go backwards also. So that gives us infinitely many solutions. That gives us negative pi over 6 plus 2 pi k as an infinite family of solutions. Now alternately, if you didn't decide to use inverse trig functions, you may have decided 11 pi over 6 was the right one to start with. You would now write down 11 pi over 6 plus 2 pi k as your infinite family of solutions. Are both of those correct answers? Yeah, in fact, they're the same answer. Negative pi over 6 plus 2 pi k is the same family as 11 pi over 6 plus 2 pi k. Those numbers only differ by 2 pi k. Nice. So let's find the second solution. So this angle was an angle of negative pi over 6. And we see that there should be some other angle
That gets us that same y value. And it looks like it's like the same angle as that, but reflected across the y-axis. What's the replacement that achieves reflection across the y-axis?
Would be negative sign. Oh, wait.
Well, no, wait, like that's pi minus theta. So I'll draw a generic picture. Instead of, if you rotate forwards by theta, and you would like to reflect that across the y-axis, that's the same thing as rotating forwards by pi and then backwards by theta. So if this angle was theta, this angle is pi minus theta. But both of those have the same y values. They have the same sign. So we can now find a second solution.
Here's the second solution. Pi minus pi over 6 is a second solution.
And I guess that should be simplified, right? Because that's the same thing as pi plus pi over 6. But that's 6 pi over 6 plus pi over 6, that's 7 pi over 6.
So 7 pi over 6 is a second solution. And so we get a second infinite family of solutions, 7 pi over 6 plus 2 pi k.
How do people feel about that? Does that seem more or less okay? Okay, so in the note packet that we're going to crack open in just a moment, we'll see even like a flow chart that'll guide you through this process. But there's one other type of equation I'd like to solve before we do that. That's an equation that involves tangent instead.
So let's try to solve
The equation tangent of theta equal to pi. And I haven't provided you a graph, but I shouldn't need to, right? You know what the graph of tangent is like. So the graph of tangent, let's describe it. What's tangent of 0?
Zero.
0, right? The slope of that line is 0.
So I'm going to sketch a graph of tangent of theta.
At 0, it's 0. And let's see, as the angle increases, the slope of this line increases, so the tangent increases, and it gets really, really, really big, and it gets to be infinitely steep. So there's a vertical asymptote. That vertical asymptote is at what angle? Pi over 2. So there's a vertical asymptote for tangent at pi over 2.
And there's also a vertical asymptote at negative theta over 2, negative pi over 2 for the same reason. So there's the graph of tangent from negative pi over 2 to pi over 2. Now how can you get the graph of tangent over the rest of the real line? Pi periodic, so as soon as you graph it over an interval of length pi, you know everything. That's probably enough. And I would like to solve the equation tangent is equal to 5. So I'll also draw a line at y equals 5. That is a perfectly straight line at y equals 5. How many points of intersection do you see between the red thing and the black thing? And in fact, there's a really simple pattern between them. If you could find this point, then that point is exactly pi to the left. That point is another pi to the left. So as soon as we find one solution, we know all. We can just add pi k. So let's describe that one solution. So think about inverse trigonometry. Can you think of a name for an angle which has tangent equal to 5? Maybe using an inverse trig function? How about inverse tangent of 5? And if you were doing this on your own time, you would want to either check by thinking about the unit circle that you keep in your head, or else by thinking about a table of values for inverse tangent to see if inverse tangent of 5 is a number that you know. But you'll find out that it isn't. So that number, you can't simplify it, you can't compute it without a machine. That's simple. So that's the solution to this equation that's between negative pi over 2 and pi over 2. So I guess that's this solution. Nice. So now that we have one, we have all of them, right? It's pi periodic, and there's a single solution in each interval of length pi. So there's the solution between that in this interval of length pi. To find this solution, just add pi. Find that solution, add 2 pi. Find that solution, subtract pi. So in general, you can just add pi k to get all of the solutions. So if you want to solve tangent theta equal to 5, well, all of the solutions are given by inverse tangent of 5 plus pi times any whole number k. How does that feel, Laura? This seems reasonable? So, I'll crack open the actual note sheet handed out today. And did anyone not get it as it got handed out? Okay. And I think instead of going through these two examples, which are in fact really close to being the same examples that we just did, I'm going to jump down to the flowcharts on the second page. If you want to solve an equation which looks like cosine of x is equal to a constant, well, first let's deal with the exception of this. There are some weird cases. So there's the graph of cosine. If I ask you to solve cosine of x is equal to 2, by looking at this graph, how many solutions should there be? None. If I ask you to solve cosine of x is equal to negative 3, how many solutions are there? None. Cosine is always between negative 1 and positive 1. So, if I ask you to solve cosine of x is equal to c for some number that has absolute value bigger than 1, the answer is just there are no solutions. On the other hand, so what we just did is, earlier, we looked at cosine is equal to a third, and we said as soon as you find 2 solutions, you found them all. So let's look at what happens when you try to solve cosine of x is equal to 1. So you get this one solution, and in fact you only get one solution every interval of 2 pi. So let's just try to describe all of those solutions right now. What is this input which gives you cosine is equal to 1? 0. What's the next input to the right where you see cosine equal to 1? 2 pi. And we didn't skip any solutions between. There's actually only one solution every interval of 2 pi. If you want to solve cosine of x is equal to 1, your starting solution is x equal to 0. The general solution is 0 plus 2 pi k, or just 2 pi k. You can do the same thing for negative 1. If you want to solve cosine equal to negative 1, well, the first angle you see where cosine is negative 1 is an angle of pi. And in fact, it's pi periodic. So you shift left, you get a solution at negative pi. You shift right, you get a solution at 3 pi, and there's nothing in between. So the general solution to the equation cosine of x is equal to negative 1, you start with the solution of x equal to pi. The general solution is x equal to 2 pi k. X equal to pi plus 2 pi k. Everyone feel okay with that? Okay, so then there's the general reasonable case. If someone gives you the equation cosine of x is equal to a number where that's an equation that actually has solutions, well, find your starting solution, inverse cosine of that number c. That gives you one of the solutions to the equation. That gives you, I guess, that one. Then you want to find the second solution, either negative inverse cosine of c or 2 pi minus the inverse cosine of c. That'll give you this solution or that solution, depending on which one you pick. And once you find those two solutions, you found them all at 2 pi k's. And if you decide you prefer 2 pi minus inverse cosine of c, this one will become 2 pi minus inverse cosine of c plus 2 pi k. So there's an algorithm now that lets you solve any equation that looks like cosine of x is equal to a constant. Do you think you should be able to do something pretty similar for sine? Of course you can. If you want to solve sine of x equal to c, if c is bigger than 1 in absolute value, well, sine is never bigger than 1 in absolute value, so you get no solution. Someone asks you to solve sine of x is equal to 7, don't do any work, because that work will involve saying the inverse cosine of 7, which doesn't exist. If someone asks you to solve inverse sine of x is equal to 1, well, you look at the graph, you see the first angle where you see a solution is pi over 2. And not only that, the solutions are just 2 pi periodic. So all of the solutions are just given by pi over 2 plus a multiple of 2 pi. If someone asks you to solve sine equal to negative 1, you'll get an initial solution of negative pi over 2. So all of the solutions will be at negative pi over 2 plus 2 pi k. That makes sense so far? Well then, if you want to solve the general case, sine of x equal to c, where c is a number that's between 0 and 1, strictly between 0 and 1, find your first solution, that's inverse sine of c. Second solution is pi minus the inverse sine of c. Simplify if possible. I asked you to solve sine equal to root 3 over 2. That's a value you actually see on the unit cell, so you should be able to explicitly say what those numbers are. And then the general solution is just take those and add 2 pi k's. That seems pretty good. If you want to solve tangent of x is equal to some number, that's even easier. Your first solution is just inverse tangent of whatever that number is. It doesn't matter what number that is, right? Picture the graph of tangent. It always has solutions.
And now the general solution is just that solution you found plus any multiple of pi. Do those instructions make sense? So let's see, with 10 minutes to go,
I think here is what I would like to do. Well, I'll give you guys a choice. So we can either go through solving some simple equations. Cosine is equal to a number, sine is equal to a number, or tangent is equal to a number. Or we can start doing things more complicated. How many people would like to see another simple example before I move on to complicated stuff? Okay, let's do another simple example. Now I'll ask you, would you rather sine, cosine, or tangent? People who would prefer sine? People who would prefer cosine? People who would prefer tangent? Okay, we'll get tangents happy. So, well, there are two good options. Let's solve tangent of x is equal to negative 8. And let's do it by reading off this flowchart. So what is this initial solution you see to tangent of x is equal to negative 8? Inverse tangent of negative 8. And let's see, maybe I'll suggest one simplification, which isn't really necessary or even that simplifying. Picture the graph of inverse tangent. Is that even or odd? Ultimately, graph the graph of inverse tangent that appears on the start of the notepad that we started yesterday. Odd. So what can I do with this negative 8 inside of the parentheses? I can pull it out, right? So here's one optional simplification. So there's the first solution. Inverse tangent of negative 8 or negative inverse tangent. Now, according to this flowchart, how can I get the general solution? Just add plus pi k to b. So the full solution then, general solution, is inverse tangent of negative 8 plus pi k, or negative inverse tangent of 8 plus pi k. That seemed pretty okay? Fair enough? Yeah. Yeah. And let's actually do one more. Let's solve tangent of x equal to root 3. Cool. So what's the initial solution that you should look for? What's the initial solution to this equation? Inverse tangent of root 3. Cool. So let's see. That should also be the angle that's between negative pi over 2 and pi over 2, which has tangent equal to the square root of 3. Is there an angle on the unit circle which has tangent equal to square root of 3 that you just already know? Pi over 3 does the trick. Everyone buy that already? Before me to draw another quadrant off of the unit circle. Okay, cool. You should always simplify if possible. So now that we found one solution to this equation, how can we write down all of the solutions to this equation? Pi. okay about that? That seems straightforward enough. So I think I want to, there's enough time. Let's solve one more that's complicated off, which is a grammatically correct construction I assert. Let's try to solve an equation like this. Let's try to solve the equation 2 sine squared of x minus 5 sine of x plus 2 is equal to 0. So let's just go ahead and take a look at that. If all of those signs were just s's, we would have a quadratic equation. So let's start with this. Maybe just for convenience, I'll replace sine of x with s. And we'll see 2s squared minus 5s plus 2 equals 0. Does that look like an equation that's easy to solve? Yeah, it's quadratic. And either you can factor it, if you see how to factor it, or you can use the quadratic formula. I'll use the quadratic formula. S is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a.
And so now I guess it's a matter of just evaluating and seeing what we get. So let's see, 4 times 2 times 2 is 16, I think. 25 minus 16 is 9. And now you see why I chose the degree 2 polynomial I did.
5 plus or minus root 9 is 3 over 4. That gives me 5 plus 3 is 8 over 2 over 4 is 2, or 5 minus 3 is 2, divided by 4 is 1/2. So I see sine of x equal to 2, or sine of x equal to 1/2.
Gesundheit. So I've solved this equation for x, so I know what sine of x is. Does that mean I'm done? No. I want to know what x is. Are those two equations each simpler to solve than the equation we started with? Okay. So we've made our life better by doing two equations. What's the solution to sine of x equal to 2? There are no solutions to that equation. What about the equation sine of x equal to 1/2? Should that have solutions? Should, right? 1/2 is in the range of sine. What's the first solution to that equation you see? Pi over 6.
Maybe I'll put in parentheses the inverse trig solution. So there's the first solution we see. How do you get a second solution to this?
Plus 2 pi k.
Well, that's out of order from what I wanted to do. So the general solution. So I'll see a pi over 6 plus 2 pi k.
And then you just subtract pi over 6 from pi.
Subtract pi over 6 from pi to find the second solution.
So this is like the first solution. To find the second solution, let's do pi minus pi over 6, also known as 5 pi over 6. So we get a general solution of pi over 6 plus 2 pi k, or 5 pi over 6 plus 2 pi k.
How do you feel about that? Seem okay? So if you see a complicated looking equation involving trig functions, try to imagine away the trig functions for the time being, solve the equation you wind up with. And then solve however many simple trig equations that we wind up with. So, I think that I'll stop. Even a few minutes on it. I'll remind you that a few things. There is a group activity which maybe is indistinguishable from a group quiz tomorrow, in which this kind of stuff will come up. There will be no class on Monday, but you should still come to this room or another one of, well, maybe not this room. You can go to one of the rooms where there is this talk happening on Monday, join us at, well, I know they don't. And there's also a math competition. If you want to sign up for it, the deadline to do so is by the time I go home tomorrow. There are sign-up sheets outside of my office. If it changes anyone's mind, it's a team competition. So if you want to sign up for teams of 3, that would be ideal. Ah, even better, I'm allowing free access to all of your notes.
I know there's a lot of
Awesome. Good. Okay, it's all done. Not a little more concept. Good.
I also don't get caught everything. Yeah, I was talking to my friend in that class, and he said that in order to prepare